Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a pleasure to have Nicole Imortica here. She's been visiting us all week. And Nicole is well known to many at Microsoft from our time she spent here as a postdoc a few years ago. Since then, she's spent a year at CWI Amsterdam, and then she's right now a professor, assistant professor at Northwestern, and so she's going to tell us about how to price information cascades.
Thanks. This is joint work with Shamka Kare and Alain Lobel, done partly while we were all visiting Microsoft Research in the New England lab. So I first, got interested in this problem from the following example, which is plagiarized unabashedly from this textbook of John Kleinberg and David Easley. So in that example, they say, okay, let's suppose that we have two urns. And either we have an urn in which and each urn has 3 balls in it. So either the urn has 2 yellow balls and 1 blue ball, or it has 2 blue balls and 1 yellow ball. And it's, there's only one urn, and it's equally likely to be either of these 2 urns. We'll call the one with more yellow balls a yellow urn, and the one with more blue balls a blue urn. And we want to play the following game, which I actually played in a lecture I was teaching at Northwestern. So the players, or the students, they come in one by one into some room, and they're going to see a random ball from the urn. Okay, so they're doing this sequentially. A person walks into the room, they see a random ball from the urn, and they also know the history of other people's guesses. So this is not the signal that the other people had. This is not necessarily the same as the ball that the other person drew, but it's what the other person guessed as to the color of the urn. So given their own private signal, this ball that they see in their urn, and the history of other people's guesses, they have to make a public guess as to what they think the color of the urn is. And in my undergraduate course, if the students guessed correctly, I gave them 1 point towards their final grade, and otherwise, they lost the opportunity for a point. They didn't like that very much. So let's try to think about what might happen here. The goal of a player, or if you're a student trying to earn points, your goal is to maximize the probability you get the point, given the information you have. And so let's think about the first person, yeah?
Is there transferable utility between players?
Grades are not transferable, I think. And in this game, no, in general.
The questions so a later player will benefit if an earlier player will give the raw.
Yeah, you might want to pay earlier people to say their true signal, for example, and then you can break down. So there's all sorts of work that goes into these information cascades. I'll talk a little bit about it. One thing that you could try and look at is paying people to do certain things.
But for now, it's just everyone's in it for themselves.
Yeah, everyone's in it for themselves. So this person sees a blue ball, and it's going to use Bayes' law to calculate the probability that they get that the urn is blue, given that they drew a blue ball. And this boy also calculates the probability that the urn is yellow, given that he drew a blue ball. And he's going to notice that the urn is more likely to be blue than yellow. And so he's going to, and a similar argument goes through if he drew a yellow ball. So he just guesses that the urn is the same color as the ball. And it's not very interesting. This hourglass is annoying me tremendously. So the second person, what's she going to do? Well, this is important. So she knows that the first guess was blue. That doesn't mean that she knows that the first ball is blue a priori. She just knows that the first guess was blue. And she knows that the first person is a Bayesian rational optimizing utility, maximizing agent, and is therefore, since he had no history, his guess mimicked the color of the ball that he drew. So she knows that the first person's guess was informative, and from that she can conclude that the first person's draw was actually blue.
So So in your class, students could use the bounded rationality assumptions on other students too.
It's a lot of fun to play games with undergraduates. They're great little guinea pigs.
Yes, but still not uniform.
So she looks at her ball and she calculates that if she drew a blue ball, it's more likely to be a blue urn. And if she drew a yellow ball, you can do the calculations with these numbers. It's equally likely to be a yellow or a blue urn. And we can say that she breaks ties in her favor. So the urn, she guesses also that the urn is the same color as the ball. Okay? Now the third person comes in the room and sees that the first two guesses were blue. And using the same sort of reasoning that I discussed about the second person, she's going to infer that the first two people's guesses were informative, and therefore the first two draws were blue. So I'm considering a history in which the first draw was blue, the guess was blue, the second draw was blue, the guess was blue. Third person knows that the first two draws were blue. And now it doesn't matter what color ball she draws. You can see that, the probability that the urn is blue, she essentially sees three independent draws from an urn, two of which are blue. So it's much more likely to be a blue urn. Much more. Well, it's more likely to be a blue urn, and therefore, no matter what she sees, she's going to guess that the urn is blue. And thereafter, when the nth person enters the room, they know that there were n-1 blue guesses. Of course, they know that of these n-1 blue guesses, only the first two had any informational content at all. So this person is facing the exact same decision problem as the third person was facing. So after two people guess that the urn is blue, every person thereafter is going to guess that the urn is blue, no matter what he or she sees. So if the first two guesses are blue, everybody thinks that the world is blue. And
the assumption is that you break ties in favor of blue.
Yeah, that's not so sensitive. If you wanted to flip a coin to break the tie, then you just need a couple more blue guesses at the beginning. So the point is that this is a constant probability, even though we have infinitely many samples from this urn, we still have a constant probability that the world is wrong.
What actually happened when you did it in your class?
Yeah, we had some information. So yeah, I had, I think, maybe, was it 5 students per? You can't do this for all 60 students. It takes too long. So I did 3 different rounds of 5 students, and in 2 of them, they got the minority color. They guessed the minority. The last person guessed the minority color. Okay, so this is an information cascade. I find this setup very fascinating, and there's a lot of questions that I'm pursuing in these directions. For example, you've all mentioned transferable utilities. So if I could pay people off, or alternatively, as the government, if I could incentivize people to be somewhat altruistic by paying you as a fraction of the population that guesses correctly, can we design systems in which a majority of the people actually guess correctly?
Once you incentivize them, they're no longer altruistic.
Well, yeah, okay, but I can say I'll pay you 50 cents if 50% of the population does the right thing. And then you have some incentive to say your true signal. We can also look at another thing I was looking at a little bit with Cephii when I was visiting this research lab last year was, you can't see everybody behind you, but only your friends. So you're given a social network. In what order should people draw balls from the urn in order to maximize the probability that everybody's correct in a fully rational reasoning setting? Okay, so anyway, this is information cascades. There's a lot of literature on this. There's a lot of examples of information cascades even in the real world. So one of the standard examples when people discuss information cascades is the choosing a restaurant in a strange town. And this is my mom's strategy. She walks into a strange town, she looks at all the restaurants, and she finds the one that's the most full, and she insists that we eat there, even if there's like a 2-hour wait, which irritates me endlessly. But it turns out that that's not just like a peer pressure thing. There is a model which would explain that she's acting rationally, being this model. And so that's one example of an information cascade explaining why one restaurant is way more popular than the others among some tourists in a strange town.
I like your first example.
Staring up at the sky. Yeah, so they actually did this in a street where some sociologist had some people stare up at the sky and see how many people stop and look up.
Yeah, I think the version in Britain is you start a queue for nothing and see how many people maybe in Soviet Russia too.
Right. So these phenomena are entertaining. There are books about funny examples. What more precisely do I mean by an information cascade? These occur when people make decisions sequentially. So the two essential ingredients are that people make decisions sequentially based on some private information, and then they take some public action, and it's these public actions that are observed by the population in general. And then we say that information cascade occurs when people start to abandon their own information, the private signals that they're getting, in favor of inferences based on other people's actions, exactly like we saw in the example at the beginning of the talk. So one of the directions that I was considering was how do we use, if we have can we use information cascades to price a product as a company in order to get astronomically large revenue? So can we leverage this phenomena to trick people into paying a lot for something that's not really worth very much? I mean, I was at Microsoft. So the setting is that we have a product here which has some value that's unknown to the people in the world and to the seller of the product as well. It's just we don't have any information about how valuable this product is, but there's some value. It's drawn. We have a distribution about the value of this product, and it's a common value setting. So this product has the same value to every user. So the users are essentially trying to learn this value and figure out how much they should be paying for this product, and the mechanism designer is also trying to learn the value. And what we have now, similar to the guessing game from before, we have a sales game where the buyers are going to enter this store sequentially, one by one. And when they enter the store, they fiddle around with the product a little bit, and they get some sense about how cool it is. And you can think about this as being like a thumbs up or a thumbs down. So this is some coarse signal of the value of the product. It's correlated with the value of the product, but it's coarser than the domain for the value, so it's not completely informative. And they also are going to see the price of the product. So and now products have a price tag with them. They get a signal, they see the price, and they also notice the sales history. They see what happened in the past, how much people were offered for the product and whether or not they bought. Then finally, the buyer is going to use Bayesian reasoning to decide whether or not to buy the product. And in this case, that means, well, they're going to look at the expected value of the product minus the price. This is what their utility would be an expectation, conditioned on the information set they have, which is their private signal and the sales history of the product. So to summarize, the sales game is that we have a sequential actions. People see a signal of the quality and the product's current price. They decide whether or not to buy, and then they decide, They see the previous actions, and they decide whether or not to buy. So this seems like the perfect setting for an information cascade, and we wanted to see if we could, get an information cascade here. In particular, we're trying to design a pricing mechanism that gives sequential prices to the buyers that's going to maximize the long-term revenue of the company. And a sort of a knee-jerk reaction for people in the field would be like, okay, let's try a fixed price, maybe the Meyerson price. Seems to be magical terminology in this field. What's the Meyerson price? You would look at the distribution for the value of the product, and based on that distribution, you can see for any particular price, what's the expected revenue of that price. Pick the one that's the maximum and charge that to every user that enters the store. So the problem with this, or with any fixed price, is that since the coarse since the signal space is coarse, you just get a thumbs up or a thumbs down about the quality of the product. It could be that a few people don't buy the product even though it's worthwhile. And then thereafter, you're going to get an information cascade, as in the Turing model, in which nobody buys even though it was worthwhile. And you're going to get a low long-term sales revenue. And by the way, I keep saying like the first 2 people don't buy, but of course, that's not really relevant. What's relevant is the differential between the people that bought and that didn't buy. So you can think about this thing, and maybe this audience likes this better, as a random walk. And as soon as the random walk hits some boundary conditions, it just flies out. So there's more settings in which an information cascade happens. It doesn't have to be the first 2 people that get the minority signals.
But don't most objects that we buy have fixed price? Doesn't this happen all the time?
There are discounts, promotions.
Those coupons you get in the mail.
Yeah, and also this is a common value setting, which so I'm in particular interested in objects that have at least a common value component, which might not be what you're used to thinking of. Okay, so we get low long-term sales revenue with a fixed price. So what? Maybe maybe you're going to get low long-term sales revenue no matter what. What should we be looking for here? What can we compare ourselves to? And the first dilemma that we have is that in expectation, the maximum revenue we can get from any particular agent is going to be at most the expected value of the product given the history that's happened so far. And I mean, this is actually really intuitive because this would be the maximum revenue that we could get ignoring the private signal that the agent is going to draw. And the private signal, this information asymmetry can only help the person who has the extra information, being the buyer in this case. So the mechanism can't get more than the expected value given the history because if we ignore signals, that's the best we could do, and the signals only help the agents. And then, of course, an immediate corollary of this is that the maximum long-term revenue we could hope to get is upper bounded by the expected value of the product, which just comes from taking the expectation over all possible histories. So it means that what we want to do as the mechanism designer is find a sequence of prices that induce the agents to learn the true value of the product in the long term. We're not going to, be able to leverage information cascades to fool people to think it's better quality than it really is. Precisely because if we did that, then there would be many histories over which we would lose because they would think it's worse quality than it really is.
So when you say we can't, you mean on average we can't, but
yeah.
If I'm a company and have, I can put out 100 different products, and it's, but it's possible that in one of them I succeed in this, right? That I get people.
It's possible that you get lucky in the history and you succeed in one.
And then from there on, that product shoots off and people are paying more than their.
But if you take the expectation over the histories, in expectation before you start, if those coin flips, if you take the expectation over those coin flips, you could.
And we start with another product.
So this is what happens in practice.
What?
Something like this happens in practice.
So your solution is to get rid of the product that has the bad history and just keep trying until you get a product that has a good history?
I mean,
version 3, right?
Yeah.
Right. Did you say? Version 3 or, Cadillac or give it a different paint job.
Yeah.
When studying instead of Henry Ford, it was his third car company which succeeded. The first two failed.
For Ford, you said?
Ford.
Also Bing, right?
We don't use the third one.
I didn't want to make that.
I don't think you're going to be able to sustain. I don't think you could even sustain a revenue above the expected true value because in some sense the agents are.
If I have a luck, that was my question, but I don't have the full picture. If I'm lucky with the first 100.
Yeah. In that history, you'll get higher than the value. Yeah, that's true.
So,
I mean, it has certainly big influence on innovative products, how the initial set of consumer, visualize the innovative products.
Yeah, so this is in some sense highlighting that.
right. So a company might consider a product where the agents actually learn the true value of failure.
Well, it's going to...
There's so many different products. A success is one where the agents learn twice the true value.
If you're going to sell one product, a priori you want to come up with a pricing scheme for this product. The maximum revenue you can get is the expected value of the product, and then you do that by having agents learn the true value.
I think the difference is this is if you can control n, right? You have the sequence of customers. Now, if you're allowed to choose how long
When
the
to
sequence
restart.
is, then you can presumably get a higher. If it's one of the cases where you have a positive cascade, you keep going, otherwise you stop.
And they package it.
Okay, so the question then becomes, how do we get agents to learn the true value of the product without losing too much revenue? And what you can see is that there's a trade-off between the prices and the information gain. And that's what I want to explain through this example here. So let's imagine that we have this product whose value distribution is the following. Either with probability 1/2, it's worth 2/3 of a dollar, and with probability 1/2, it's worth only 1/3 of a dollar. And again, this is a common value for every agent. So let's look at the first buyer, and suppose that the price tag of the product is 1/3 of a dollar. Now, the first buyer might get a high signal, a thumbs up, and think, oh, it looks like it's worth, a low signal, thumbs down, and say, oh, it looks like it's only worth 1/3 of a dollar. But the price is also 1/3, so the agent will buy. Alternatively, might get a high signal, a thumbs up, and say, oh, it looks like it's worth 2/3 of a dollar. And it's only priced at 1/3 of a dollar. So again, I'm going to buy. And in either case, the revenue is 1/3 when we price at 1/3. Alternatively, we could have priced at 2/3, and now with probability 1/2, the signal of the agent is low, and he doesn't buy. Whereas with probability 1/2, the signal is high, and he buys. And so our expected revenue is again 1/3 of a dollar. Right? But there's a difference between these two prices. What's the difference?
History's changed.
Sorry?
History.
The history, exactly.
Living in the future.
Or the future, depending on whether you're looking forward or back. So with price of 1/3 of a dollar, the second buyer knows nothing about the first buyer's signal, because no matter what the signal was, the guy bought. Whereas with price 2/3 of a dollar, we still get the same revenue, and the second buyer gets to know the first buyer's signal, whether it was high or low, from which he can make inferences about the value of the product. So the mechanism's price determines the informativeness of the signal. And now let's think about the second buyer. Let's suppose that the first buyer, she inferred that the first buyer had a high signal. Okay. Now we can consider pricing the product at $0.50. And if she gets a high signal, and she knows the first buyer also had a high signal, then she's going to think that it's likely to be worth more than $0.50, and so she's going to buy it. On the other hand, if she got a low signal, and the first buyer, she infers that the first buyer got a high signal, it still looks like an expectation. I mean, you can do the calculation. I didn't do it here, but she's still going to think that it's worth, the expected value is $0.50, so she'll buy it. And the revenue is $0.50. If we price at 2/3 of a dollar, with probability 1/2, she's going to buy it. And with probability 1/2, she gets the low signal and she doesn't buy it. So the revenue is 1/3 of a dollar. So what happened here was that the price that was informative, being the higher price, had a lower revenue than the price that was so to maximize revenue, we should have charged a lower price, but then everybody would have bought, and we would have gotten no information gain. Whereas by charging a higher price, we lose revenue, and we gain information. So here's the key difference. With a price of 1/2, the revenue is 1/2, which is higher than the revenue with a price of 2/3. Revenue with a price of 2/3 is just 1/3. But with a price of 1/2, everybody's buying, so it doesn't differentiate the signals of the agents based on the history. Whereas with a price of 1/3, the third buyer is going to be able to infer that the first two signals were high and buy. So this shows that there's a trade-off between gaining information and gaining revenue. Okay, so in general, we can think about the following picture. We have the sliding scale about the price that we can choose to charge as the mechanism designer. And for low prices, any signal type is going to buy, so there's absolutely no information gain. For very high prices, no signal type is going to buy, so again, there's very little information gain. But there's this nice intermediate region where the prices are informative. Yeah?
Stupid question. But is the mechanism designer allowed to determine the price according to the history? Can he look at it?
Yeah, I am using it here. So every day I post a new price. Okay, so, and everybody sees the history. The history is public to the designer and all the agents. Yeah?
So the information here is, what's the goal? The goal is to inform everyone else that the product is valuable, or to gain information about what?
You want to learn the true value of the product. So essentially we're setting up a martingale here.
Wouldn't you rather convince others that it's valuable? So you'd price your product high and then hope enough people buy it to keep it there?
Yeah, so we're showing that this can't achieve, you can't get better than the expected value through such a strategy in revenue.
Restricted to one product.
But why can't you do what the Bayesian thing with like the history? You have the history.
Okay, so that's going to be exactly so the Bayesian price in this example was the 1/2. So you don't gain information after a while if you keep using Bayesian price.
You make the most money.
No, because the product might really be worth 2/3, and you can eventually learn that if you let them try and differentiate.
It's kind of greedy, so in the reverse way. Yeah. So one thing about that graph, we showed something like that in TechFest when Craig Mundy came by and said, "You don't understand. People will not buy a Jaguar if you sell it too cheap."
Will not what?
Will not. Some people. For some things, having a high price is attractive.
People have an estimate of the quality based on the price that you offer it at.
Or they want to signal to others that they can afford this high price.
Actually, it is for restaurants, it's a major signal in a new town, in a strange town.
Yeah. Higher price, like if you go to the higher priced restaurant, you look cool because you sit in the window.
No, you hope that
people know you're rich.
No, but if you just price higher without making the product exclusive, but it's not a good signal. If tomorrow Honda starts selling, okay, our car is $70,000 instead of 17, nobody will buy it.
They bring out a new brand. They call it.
So they have to spend that kind of money to make.
Sorry for the.
No, it's a nice small audience. We can have an informal discussion.
Yeah, but we have a deadline.
I have a deadline. You have a deadline.
Yes. The audience might be leaving.
It's okay. The talk is only 45 minutes long, so we're almost done. Okay, so so there's a trade-off between gaining information and gaining revenue. The Bayesian price is not, even if you change it every day, it's not going to necessarily do the right thing in terms of information. So back to this picture, we can also plot the revenue curve as a function of the prices. And this is showing you that the price that maximizes the revenue on this given turn might not be informative. It's going to be in general somewhere, like the yellow curve and the blue curve are different. And by information curve, I don't have a precise mathematical meaning here. It's just some intuitive picture. Okay, so in the two signal case that we were discussing earlier, I can actually Why doesn't that show up? Oh, okay. I can actually look at the two special prices on this picture, being this price here, which maximizes the yellow curve, and that price there, which maximizes the blue curve. And these are the explore and exploit prices. And we have a characterization theorem that says any optimal mechanism is going to charge informative prices infinitely often. So it's going to give agents enough samples on which to learn. Informative prices are those ones that actually differentiate the signals. And then it's going to charge the revenue maximizing prices, those sort of instantaneous Meyerson prices, on a sufficiently dense set of agents in order to exploit the revenue. So any optimal mechanism has to look like this. And the question then becomes, in what way do you want to trade off the information gain versus the revenue gain?
And you have to separate this?
In general, yes, because as I showed in that picture, the revenue gain might not be an informative price at all. And of course, you need to charge revenue gaining prices. So intuitively, you need to do this in order to learn. And we showed that any optimal mechanism learns. And you need to do this in order to exploit the agents and get that revenue that you could get. Right, that's the picture I was looking for. So we have in the two signal case, we can talk about the exploit price and the explore price. And we can consider a mechanism which the explore price is going to be the expected value given the history. So now precisely only high signals by in the two signal case with this price tag. And the exploit price is the thing that gets you the most revenue. And then the explore-exploit mechanism is going to explore infinitely often a vanishingly small fraction of the time and exploit on all other rounds. And what we show is that this mechanism has a long-term average revenue equal to the value. So this is equal to the value. An expectation, it's getting the expectation of the value, but in fact, it's actually equal to the value. So that's a slightly stronger statement. And the reason that this is true is because the beliefs are going to converge to the correct value by martingale properties and the fact that we're exploring infinitely often. And then we exploit most of the time. So once we finally get there, we're getting the value. Furthermore, this is optimal in terms of maximizing revenue. And that was by the theorem that said we can't get more than the expected value. This mechanism is getting the value, which is at least the expected value. And finally, we can find the optimal explore-exploit schedule, which minimizes the regret over all mechanisms. So if you might stop earlier in the sequence, you want to not have too much regret with respect to the optimal mechanism up until that time in a multi-arm bandit sort of setting. And in order to minimize the regret over all mechanisms, you just need to do this optimal trade-off between explore and exploit. And that turns out to be t to the 2/3. So for those of you that know. So if you want to explore t rounds, you should exploit. If you want to have t people enter the store, you should exploit t to the 2/3 time. And that turns out to be the optimal regret in this setting. So if you don't know any multi-arm bandit stuff, that probably doesn't make sense, but we have a proof of this I can show you later if you're interested. So there are a lot of issues that you might have with this model. You guys mentioned some, which was that you might have restarts that we don't allow. Other issues are that the prices we're assuming are public, and in fact, that seems a little suspect. You might have, in a real setting, you could perhaps have a sense of what the sales of this product are like and how successful this product is, but knowing also the pricing trajectory of the product might be a more suspicious thing. So we think we can accommodate private prices and also get rid of the common value assumption. So long as you have correlated values, they don't have to be completely common. And so that's the varying types. And let me just skip that. We can also look at the issue of partial observation. So you don't observe the entire history of the product, but you only know whether your friends bought or not. And so then you need to start thinking about the graph structure in the information cascade setting. So that's all I have. And take any questions.
Any more questions?
So,
Yeah.
a basic question, maybe even in the original balls in the bag. If, for example, 1% of people haven't understood the rules and they just report the color that they see, and the other 99% are rational, and everybody knows this.
And everybody knows which type you are.
Well, yeah, I mean, the 1% don't know anything, right? They just do it. Yeah, so it's, yeah, it'd be like everyone knows what type they are, and everyone knows this figure. What happens? Is it the same, or is it? I was trying to see how robust is this.
It's not very robust at all. So this would break it. Especially, I mean, it's obvious that it would break it if I know who's
But if you don't know, it's interesting. There might be a transition.
Yeah.
Critical problem.
Yeah, I mean, you don't know the individual people. You just know. I know I'm rational, and
you don't know who's who.
Yeah.
Yeah. If you don't know who's who, then.
If you know what fraction they are, then if you suddenly see 0.2% yellows, you realize that that's the reason for that.
Except that, well, that would be true if all the rational people had been saying blue. But so if everyone's like this, it's not quite so clear, right?
Because previous people will be using these considerations as well.
Yeah, but at some point you cross the phase and then.
See, one thing is that you can always infer who's irrational. I mean, the irrational people are the people that didn't understand the rules are going to be doing something that doesn't make sense based on the history, right? Yeah, saying yellow when it should be blue. So.
Yeah, I mean, I just consider lots of things, but I mean, what I suggested is the 1% just report the ball that they got. As simple as that. And the 99% are fully rational and know that this is what's happening.
So, you see, if you're saying people can infer, then you won't get this string of rules.
I mean, this was a reasonable suggestion, right? That it behaves the same until some point, and then suddenly people can see. So that's maybe.
Yeah. Oh, that's a great variant. So sorry, I missed part. Did you talk about the transferable utility? What's the optimal thing to pay?
I don't actually know. So all of these are infinite population models, but we're looking at this question in a finite population model where you want to pay for some fraction that gets it correctly. And so at the end of time, there's some end of the time. And now everybody gets a rebate based on the fraction of the population that guesses it correctly. This is one variant I thought of. Another.
But just, I mean, even if it's potentially infinite, just in your version, the fourth person will want to pay the third person something so that they reveal,
Yeah, you can also ask
information.
this question. I don't know what goes on in that setting either.
And there hasn't been, you don't know of any work on optimizing that?
I don't know about the transferable utility setting. The question about the fraction of the population, I've seen some similar things. I don't know a lot about information cascades. I just basically read this chapter in that book, and then Elon did a thesis on it. So that's why I was talking to him about this problem. Yeah?
Do you assume that prices without the decisions bear no information for future buyers. So somehow, if you get used to the idea that this object that should cost this much, even if you believe that it should be worth twice as much, it will be hard to sell it. So even if you believe that...
You mean like I won't buy it even if I think it's worth the price because I'm upset that you charged me more than
because
my
you
friend?
expect that that's why you have to repackage Toyota as Lexus before you can charge 50K for it. Even if you believe that it's worth.
Yeah, I don't know how to incorporate this in a rational utility model.
Or you may just...
So for one thing, you only walk
drop.
into the store once here, right? So if you pass it up because of some...
But if you know that, okay, this is the exploration day, today everything is double, you'll come back tomorrow.
Yeah, you only get one chance here. And if you start to allow people to try and time their arrivals or be strategic about that, then of course you're going to get people, wanting to come later when the value is more certain.
So the conclusion the seller wants the buyers to learn the true value, and that was the consequence of this one product assumption. So if I have a version where I can restart and sell a new product or just
and also it's also the consequence of the universal value, that it's the same value for everybody.
And you don't even need to think about restarting. You can just phrase it as you can decide to stop. And that comes to the same thing. You just have a horizon that's determined by the store owner.
Right, but you should then incorporate some cost of scrapping the product. But I think that's really one of the real differences between this model and what the real life is trying to capture. That products get started and get scrapped all the time when they're not successful, and maybe it's because they're bad, or maybe because the first few coins didn't land right.
I just had a thought about the earlier conversation we were having, which is that if you allow me to transfer utility and you have an infinite population, then I can just pay I want an infinite subsequence to be announcing their true values, right? But that infinite subsequence can be very sparse. So certainly I'm going to have enough money from all the other people to pay off that.
So you can, the infinite subsequence could be the 100 first people.
Yeah.
Yeah, no,
Or you could even get something approaching one if you do
Sure, it can approach one, but the question is more about rates. So as n grows, how fast can you do and how fast can you approach will you want to pay? If you're the hundredth person, how will you want to divide your payment between the previous ones? That depends on how they divided their payments.
Alright, let's thank Nicole again.